Okay, so part two, starting off with number four for numerical methods for partial differential equations practice final exam. So consider u sub t plus a u sub x equals 0, where a is greater than 0. Use the first order upline scheme. So u sub j n plus 1 minus u sub j n over delta t plus a u sub j n minus u sub j minus 1 n over delta x equals 0. Here we go here for A, derive the CFL stability condition. Part B, compute the local truncation error. Part C, show that the leading error term acts like artificial diffusion. Part D, derive the modified equation up to second order terms. And Part E, explain why the standard explicit scheme for advection is unstable. So this is advection, equation, and numerical diffusion. So here we have u sub j n plus 1 equals u sub j to the n minus nu u sub j n minus u sub j minus 1 n, where nu equals a delta t over delta x. We insert u sub j n equals g to the n e to the I j theta. Then g equals 1 minus nu quantity 1 minus e to the negative I theta. Therefore here, absolute value of g squared, that equals quantity 1 minus nu plus nu cosine that whole quantity squared plus nu sine squared. After simplification here, our absolute value of g squared equals 1 minus 2 nu times 1 minus nu times 1 minus cosine theta. And stability requires 0 is less than or equal to nu is less than or equal to 1. So going up here for the truncation error, we use Taylor expansion. U x comma t plus delta t minus u x comma t over delta t equals u sub t plus delta t over 2 u sub t plus order of delta t. And u x comma t minus u of u x minus delta x comma t over delta x equals u sub x minus delta x over 2 u sub x plus order delta x squared. So we could say from here that tau equals u sub t plus a u sub x plus delta t over 2 u sub tt minus a delta x over 2 u sub xx plus order delta t squared plus delta x squared. And since u sub t equals negative a u sub x, then u sub tt equals a squared u sub xx. Our leading error is this a squared delta t over 2 minus a delta x over 2, close parentheses, u sub xx, that equals negative a delta x over 2, 1 minus nu u sub xx. So our modified equation is u sub t plus a u sub x equals a delta x over 2, quantity 1 minus nu u sub xx plus order delta x squared comma delta t squared. So we could say here that the centered explicit scheme has amplification g equals 1 minus I nu sine theta. So absolute value g squared equals 1 plus nu squared sine squared theta greater than 1 for most modes. So it is unstable. Okay, so that's for number 4. Pardon me if I mispronounced anything. And I don't know if I read this part. This leading correction is artificial diffusion. Okay, and number 5. For u sub t plus a u sub x equals 0, derive the Lax-Wendroff scheme using Taylor expansion in time. Parts A, B, C, D, and E. Obtain the update formula. Determine the order of accuracy. Perform the von Neumann stability analysis. Compare its behavior to upwind for smooth and discontinuous data. And explain the difference between numerical diffusion, numerical dispersion. So Lax-Wendroff scheme or Taylor expansion is here. Okay, our u x comma t plus delta t equals u plus delta t u sub t plus delta t squared over 2 u sub tt plus order delta t cubed. And for u sub t equals negative a u sub x, then u sub tt equals a squared u sub xx. So u sub j n plus 1 equals u sub j n minus n. U sub j n plus 1 equals u sub j n minus a delta t u sub x plus a squared delta t squared over 2 u sub xx. So we use center differences. U sub x is approximately u sub j plus 1 n minus u sub j minus 1 n over 2 delta x. And our u sub here xx is approximately u sub capital U sub j plus 1 n minus 2 capital U sub j n plus capital U sub j minus 1 n over delta x squared. So it is second order accurate order delta t squared plus delta x squared. Von Neumann analysis gives g equals 1 minus I nu sine theta plus nu squared cosine theta minus 1. And stability gives absolute value nu is less than or equal to 1, and compared with up is more diffusive and smears sharp fronts. So our LW is sharper for smooth solutions, but may create oscillations near discontinuities due to numerical dispersion. Numerical diffusion happens to dampen amplitudes, and numerical dispersion changes wave speeds depending on wavelength. So again, numerical diffusion damps amplitudes. Numerical dispersion changes wave speeds depending on wavelength. So diffusion, dispersion. Sorry if I didn't, if I wrote this kind of sloppy. That's number 5. Moving on to number 6. So consider the boundary value problem here. U double prime x of x equals f of x, where 0 is less than x is less than 1, with u of 0 equals u of 1 equals 0. Derive a standard second order finite difference discretization for number 1. For letter A. For letter B, write the resulting linear system. Letter C, show that the coefficient matrix is symmetric, positive, definite. Letter D, estimate the condition number as delta x approaches 0. Discuss how the condition number affects iterative solvers. So this is a Poisson equation with finite differences. So for negative u double prime equals f, we use negative u double prime of that x of j as approximately negative quantity capital U sub j plus 1 minus 2 capital U sub j plus u capital U sub j minus 1, that whole numerator over h squared. So 2 capital U sub j minus capital U sub j minus 1 minus capital U sub j plus 1 over h squared equals f sub j. So the matrix system here is AU equals F, where A equals 1 over h squared times the following entries for the respective rows and columns. For the so here, for any v transform AV equals 1 over h squared, and the sum here of v sub j plus 1 minus v sub j squared greater than 0 for non-zero v satisfying homogeneous boundary values. And hence, A is symmetric, positive, definite. The eigenvalues are lambda sub k equals 4 over h squared sine squared of k pi over 2 times the quantity n plus 1. So we could say here that lambda sub min equals order 1, lambda sub max equals order h to the negative 2. So kappa of A equals order h to the negative 2. As h approaches 0, the system becomes increasingly ill-conditioned. And we could say iterative solvers converge more slowly unless precondition or multigrid is used. Okay, and now from here, number 7, that's number 6. Okay, number 7, consider the following, that negative delta u equals f of xy on the unit square with homogeneous Dirichlet boundary conditions. Part A, B, C, D, and E. Respectively, derive the 5-point stencil. write the matrix equation, describe the sparsity pattern, estimate the number of unknowns and non-zero entries for that n by n grid. E, compare the cost of sparse direct factorization, Jacobi, Gauss-Seidel, SOR, and conjugate gradient. So this is a two-dimensional Poisson equation, and for negative delta U equals F, the 5-point stencil is 4 U comma U sub I comma J minus U sub I plus 1 comma J minus U sub I minus 1 comma J minus U sub I comma J plus 1 minus U sub I comma J minus 1 over H squared. And that is equal to F sub I comma J. So the matrix equation is AU equals F. The matrix is sparse, symmetric, positive, definite, and block tridiagonal. Each interior point couples to itself and its 4 nearest neighbors. For n by n interior grid, the number of unknowns is n squared. The number of non-zero entries is approximately 5n squared up to the boundary corrections. The cost comparison, sparse, direct factorization, order n squared per iteration in 2D. For SOR, order n squared per iteration, faster convergence. For Jacobi, Gauss-Seidel, order n squared per iteration, and for CG, order here n squared per iteration, often much better for SPD systems. So we could say with good preconditioning or multigrid, one can approach nearly optimal order n squared total work. Okay, so that's number 7, and that's part 2. Thank you and have a great day.